Okay, welcome to video number 11 of the Diaries of a Coronavirologist YouTube channel. Today is the 7th of April, and we are up to about 1.4 million confirmed cases of COVID-19 and a little bit over 81,000 deaths. Now, every video I put these numbers up just to date things and keep everyone aware of where we're at. But you may notice I always say confirmed cases of COVID-19. And today's topic is going to be about testing and how those numbers, those confirmed numbers, are generated. Firstly, though, I just want to say a massive thank you to everyone who's been subscribing and sharing this channel and commenting and engaging with it. It hit over 1,000 subscribers at the weekend, which was pretty cool, so thank you. As I say, tonight's topic is going to be about testing. There are a lot of criticisms that could be leveled about the testing and how it's all gone through in various places around the world. But I don't want to go into that. I want to just talk about the science. I want to explain what the PCR tests are, and I want to talk about what the serology tests are and give you the science behind these. I'm also going to try something new tonight because I can actually show you a little bit more about PCR, being that I ran an experiment that involved PCR earlier. So you'll get to see another angle of the lab. So the first of these tests is the PCR test, or QRT-PCR, or RT-PCR, or qPCR. I'll probably use all of those kind of interchangeably a little bit. But what that all breaks down to, so QRT-PCR is quantitative reverse transcription real-time polymerase chain reaction. So here, samples are taken from someone who is thought to be actively infected with the virus. That's an important part of this test, is you need to be actively infected. So samples get taken from the nose or the throat. Those swabs get taken and placed into preservative liquid from which you can then extract all of the RNA. So those samples will have cells from your own body, they'll have bacteria, and if you have a SARS2 infection, they'll also have the virus. So you extract all of the RNA from all of that, and you've just got this big mesh of RNA from which you can then hunt specifically for SARS2 genomic material, the genome being made up of RNA, of course. But the first step is to convert that RNA into DNA because the polymerase chain reaction uses DNA. So this is a process known as reverse transcription, something HIV is famous for example. So HIV has an RNA genome that it converts into DNA through reverse transcription, and it inserts that DNA into cells of the human body to infect them. So we take advantage of that in the lab and convert the extracted RNA into DNA. And this DNA can then be used to hunt for signatures of the SARS2 genome. So the way the hunt is performed for the SARS genome within the sample at this stage is using something known as primers. So these are short stretches of DNA, about 20 bases or so, that are complementary or matched to stretches of the SARS genome that are in principle unique to that viral genome. So a way to think about this is, let's say you have a Word document and you want to find a specific word. You can use the command find or control find, depending if you're a Mac or Windows user, and type out the specific word you're looking for, and then you'll find all the instances of it within a big document. That's kind of akin to what the primers are doing. So in the PCR reaction, those primers will find the bit that they are matched to in the SARS genome, and then a DNA polymerase that's in the reaction will amplify that stretch of DNA, this unique part of the SARS genome that is the probe for seeing if SARS2 is present in the sample. So to use my word analogy, that would be like copying and pasting that word you've searched for over and over and over again. Now, at the same time as copying that word, you're also highlighting it. So in the PCR reaction, what that equates to is there are fluorescent molecules that start to intercalate, going between the DNA, and therefore a fluorescent signal starts to build up and amplify in the sample. And this is what gets detected to tell you if you have this specific stretch of DNA that is evidence of the SARS2 virus. And as I said, I can use some props tonight to show you what that looks like. So come with me on a walk in the lab. So a slightly different view of the lab. I'm just on the opposite side of the bay. And this is what a PCR machine looks like. For example, there's different looks, but this is the one we have. So the samples go in here, this little tray at the bottom, and then all that stuff I was talking about gets run, and you get something that looks like this at the end. So all of the red lines going up are evidence of amplification of DNA. And once they hit a certain threshold, this horizontal line, that's when you can tell that there is this DNA present. And what you're looking at specifically is that these are evidence of there being significantly more DNA in the sample and these being significantly less, which is good because it suggests that my experiment worked. I will add that that was actually a SARS2 experiment, so that's quite good. So that brings me to serology testing, which is the second type of testing being used in the SARS2 outbreak. So for serology testing, what you're looking for are antibodies. Now the difference here, an important difference, is serology testing doesn't necessarily show an active infection. Antibodies can take 3 to 5 days, maybe a week, maybe even 2 weeks to come up to detectable levels, at which point the virus could have left the body. Antibodies stay around a lot longer than RNA typically. And therefore, serology testing allows us to tell if someone has been infected. And because you're looking at antibodies that are targeting the virus, you can get a sense of whether that person may be immune. So while these two tests look for different things and show you different things, combined, they can potentially be very powerful for us working out how best to combat this outbreak. Knowing who is infected and how many people are infected is very good for us to help isolate appropriately and give treatment where necessary and all these sorts of things. And knowing how many people have been infected is potentially a way for us to get back to normal. So if there's a lot more people who've been infected than we realize, then we're getting much closer to the level of herd immunity, which might allow us to stop social distancing. There's generally a thought that if about 70% of the population become infected, this is a level where viral transmission will become much lower and we can start to deal with this more effectively than this surge that we're trying to protect against by socially distancing. Moreover, knowing who has been infected and who has good levels of antibodies is also a good way for us to move forward with the convalescent plasma treatment. I talked about those in a previous video, so you can go back and check that out if you're not sure what I'm talking about. But if we know there's a lot more people who have antibodies and that therapy is found to be effective, then that's a really good way that we can get samples and use it as a treatment. So that's testing, serology testing and PCR testing for SARS2. I've used SARS2 specifically, but it's the same principle for any kind of virus. The same aspects apply. And I also showed a little bit more of the day-to-day life in the lab, keeping with the diaries aspect. So thank you for tuning in. As always, please stay safe and wash your hands. Keep following all the recommended guidelines. And please keep sharing the channel. I appreciate that I've hit over 1,000 subscribers. I didn't expect to hit that when I started this, to be honest. So I very much appreciate it. Thank you for watching.